Welcome to this presentation. We'll be looking at space trusses or 3D trusses and how we can verify our results of our analysis. Again, we're going to focus most of our analysis here on ANSYS or in ANSYS for two examples. I'll do one example in this presentation and another example in the next one. And so what we need to do with 3D trusses, like we did with our 2D trusses, is we need to shift from our element or body fixed frame of reference, our local reference, and expand that, or from our local coordinate system, to our global coordinate system. So from local to global coordinate system. The way we can do that is with looking at these angles and finding overall cosine theta x. So figuring out how we can get this cosine angle here, and figuring it out from the 2x components divided by L. And we can do the same thing with the cosine of theta y and the cosine of theta z. Get those displacements as well. All this information feeds into determining how we can get our global coordinate form of our local coordinate form version of our stiffness matrix. So again, we're using these transformation matrices, but not the same ones we had in 2D. We have to use the 3D matrices, and that's what this guy is. So this is our big old 3D transformation matrix, but this is again the global coordinate form of our stiffness matrix. Right, so that's what that looks like generically for any positioned member in space. Because we need not just one theta, we need three different thetas to find how it's located in space. All right, so if you're doing this by hand, you would use this matrices, but again, I just want to give you that information. Pretty much all the rest of the steps are the same. All right, so let's focus on the verification or results for a bit here. One of the things we can do to verify our results is we can check our reaction forces. So in this case, we have the triangle, similar setup to example we've looked at before. But if we're fixed here at node A and at B we had a rolling joint, so we're just no motion in the y direction. If we will look just at the forces, the sum of the forces in the x direction, all we have is the 100 pounds, and then we have this reaction force at node A. And we can quickly find that's equal to the reaction force at node A in the x direction is negative 100 pounds. Do the sum of the forces in the y direction, we'd have a function of A and B, y components at A and B. And so that we wouldn't have enough information to solve, but if we also use the moments, some of the moments about node A, we could then find what B is and use that ultimately to back solve what A is. All right, so that's one way we can do quickly some hand calcs and evaluate those against what we actually come up with in our analysis. The next form or way we can verify our results is look at the sum of the forces at each node, which should be 0. So here's node 2 in the bottom right hand corner of our triangle. So we have this reaction force of 86.6 pounds, and so if we look at our two forces, they should work out to cancel that out. So again, sum of the forces in the x direction, we get the force in the negative x direction, so negative force 1 with an element 1, and we also have the direction of the x component of an element 2 going in the negative direction, so we have force 2 cosine 60 equals 0. And then look at the sum of the forces in the y direction, and I don't have any components for element 1, but we do in element 2, so we can ultimately solve for the force in element 2 and making sure that's what it should be. All right, another option we have for verifying the results is number 3, pass an arbitrary section through the truss and analyze that. Right, so we got the 100 pounds at the top here. We draw an FBD. We got the 100 pounds. And we got the force in element 3 and force in element 2. Do the sum of forces in the x. And we can include the sine components of our two forces. Sum of the forces in the y. And we just have the y components of our two forces and the cosine of those. And if we need to, we could use the sum of the moments about a node to solve for that, but we have two equations, two unknowns with this case that would be done. All right, so 3 different ways that we can verify results, which is always good because if we didn't put in have the right setup for our ANSYS or any type of analysis, we want to make sure that we can look at our overall results and get a sense if we're on the right path or not.